Let's use the formal semantics of NOR to describe the reduction of this lambda calculus expression. Specifically, this expression is add 1 and 1. That is to say, we should get 2. 1 plus 1 is 2. Both ones are of course expressed in church numerals, and this definition of add is what we used in Module 2. Here are the semantic rules we defined for NOR. And since these rules use substitution, here is the definition of substitution from Module 2, specifically the version that can avoid variable name clashes. As it happens in this reduction, in spite of having similar variable names, we won't actually have any clashes, so it wasn't that important to use the correct version, but, well, it is the correct version, so we used it. In addition, I'm going to name each of the productions so that we can specify which production was used, or which productions were used, for each step along the way. The productions are rules of our semantics. There are semantic rules, so I'll usually be calling them rules rather than productions, but those terms are interchangeable in this context. Essentially, arrow is a step of reduction or execution. So at any point, what we're trying to answer is the question, what can go to the right of an arrow, where our previous state is to the left of that arrow. I'm going to put the arrow itself on a new line just to make room, because we'll be doing several of these steps, and it wouldn't fit horizontally across the screen. When deciding what rule to take, the first thing to do is to see if the conclusion of any rule can possibly match our expression. In this case, our full expression is an application. The rator of that application is also an application. Remember that applications bind left to right in the lambda calculus. And the rand of that application is an abstraction. The conclusion of the application rule cannot possibly match because it's the application of an abstraction to any expression. And our application's rator isn't an abstraction, it's an application. The reduce left and reduce right conclusions could both match, since they both match any application of any rator to any rand. But now we need to see if the premises apply as well. The reduce left rule has two premises. Let's focus on the second premise first. This is a universal quantifier, which says that for any variable name, for any expression, M1 is not a lambda of that variable and that expression. Put informally, what this is saying is that the rator of this application is not an abstraction. If the rator were an abstraction, then the application rule would always match, because it matches any abstraction. So this premise simply excludes the reduce left rule if you could have instead used the application rule. That is to say, this premise is, if M1 was an abstraction, then don't use this rule. The first premise to the reduce left rule is that M1 itself reduces to M1 prime. Note that M anything is a metavariable here, so there is actually an implicit existential quantifier here, since there's nothing else to restrict what M1 prime means. That is to say, what this is really saying is that there exists some M1 prime such that M1 reduces to that M1 prime. In other words, all we're saying here is M1 is reducible, and specifically it reduces to M1 prime. M1 in this case is this sub-expression, which is an application, in which the rator is an abstraction. The application rule matches applications with abstractions as rators, and it has no premises at all, so this premise of reduce left is certainly true. Therefore, reduce left does apply, but before we can work out what M1 prime is, and well, apply reduce left, we have some more work to do with the whole expression, because it matched the conclusions of reduce right as well as reduce left. The question is whether it matches the premises of reduce right as well. Well, the first premise is that M2 is reducible, and from the abstraction rule, it at least might be, because the rand M2 is an abstraction. As it happens, it's not really reducible, but we can use other rules to show that reduce right doesn't apply anyway. The next two premises are quite important. The third premise is that M1 is not an abstraction, just like a similar premise in reduce left. M1 is certainly not an abstraction because it's an application, so this premise holds. The second rule is that M1 is not reducible. That is, for every possible expression, M1 does not reduce to that expression. Another way of saying this would be that there does not exist an expression such that M1 reduces to that expression. But in showing that the reduce left rule applies, we showed that M1 is reducible. That was the first premise of reduce left. Since this premise requires that M1 is not reducible, the reduce right rule does not apply. Indeed, this premise guarantees that the reduce left and reduce right rule can never both apply, because this premise is the exact inversion of the first premise for reduce left. All of the universal quantifiers in these semantics, our semantics for NOR, are only to guarantee this kind of ordering. Now we've decided that the reduce left rule applies, but we haven't resolved what M1 prime actually is. And we can't apply this rule until we know what M1 prime is, because it's part of our conclusion. M1 matched the application rule, so M1 prime is the right-hand side of that arrow, the arrow in the application rule. According to the application rule, we should substitute the lambda variable for the rand in the body of the lambda. That's how you do an application. Take the body of the lambda, substitute the lambda variable for the argument, the rand. This substitution is a very simple case, since the variable name m appears nowhere else, so we substitute m for the rand, which was the church numeral encoding of 1, and in this sub-expression we get this substitution. We're not quite done yet. That was the M1 prime in the reduce left rule, which simply said that in an application, we may reduce the rator and keep the rand unchanged. Well, we just reduced the rator, so let's keep the rand unchanged, and our final expression is this. To keep this video from being infinitely long, I won't go into quite as much detail for the rest of the steps. Once again, our expression is an application, but this time the left is an abstraction. Both the reduce left and reduce right rules explicitly forbid this case. They will not be used if the left was an abstraction, if the rator was an abstraction. So the only rule that matches is application. We substitute n for the rand, which was the church numeral encoding of 1, and we get this. Now our expression is an abstraction, and we only have one rule for reducing abstractions, the abstraction rule. It matches if the body of the abstraction itself can be reduced. The body is also an abstraction, so we just do it again. Now we have an application in which the rator is an application, and the rand is also an application. That means the rator is reducible, so we use the reduce left rule. The rand is also reducible, but the reduce right rule explicitly forbids the case when the rator is reducible, so we can only use reduce left. Now we have an application in which the rator is an abstraction, so it matches only the application rule. That rule says to substitute this f for this f in the body of this abstraction. But in fact, substituting a variable for its own name doesn't do anything. Again, we have to use the abstraction rule twice to get into the body. And now we have an application in which the rator is an abstraction, so the application rule matches, since it requires that the rator be an abstraction, and neither reduce left or reduce right match because they explicitly forbid that case. We substitute x for this entire rand. We're not quite done yet. Once again, matching the abstraction rule twice, we need to decide if this body can be reduced. This is an application in which the rator is a variable and the rand is an application. The application rule doesn't match because the rator is not an abstraction. The reduce left rule doesn't match because the variable is not reducible. But the reduce right rule matches if the left isn't reducible, or an abstraction, and the right is reducible. So now, finally, we reduce the right because we found an application where the left wasn't an abstraction and wasn't reducible. This expression is an application in which the rator is an application and the rand is a variable. So we reduce its left, its rator. Finally, we have an application of an abstraction to a variable. Once again, the variable name is the same, so we use the special case of substitution and use the body verbatim, getting this. This is a very similar case: abstraction, abstraction, reduce right, and then we have this expression. Once more, we can apply the application rule with the special case of substitution where the variable name is the same. Now, the conclusion of the abstraction rule does match this expression. But the rule only matches if the premise is true as well, and the premise is only true if the body of the abstraction is reducible. The body is also an abstraction, which again only satisfies the abstraction rule if its body can be reduced. This expression only satisfies the reduce right rule if the rand can actually be reduced, and this expression matches no rule at all. It's just the application of a variable to a variable. So our chain of premises is broken, which means our expression cannot be reduced any further. The abstraction rule almost applied, the abstraction rule almost applied to its body, the reduce right rule almost applied to its body, but because there was no reduction we could take with just fx, none of those rules actually applied. Thus, we conclude that in NOR, our original expression reduces to lambda f dot lambda x dot f paren fx end paren, which is the church numeral encoding of the number 2. 1 plus 1 is 2.